Well, hello everybody, welcome back. So this is class 4. We're going to dive right into. Hope things are going well with the labs and the understanding of the lectures is good. So there was a discussion board request for an audio transcript, and unfortunately I don't have that. I hope that YouTube, the closed captioning, the automatic closed captioning is sufficient and allows for a transcript of what I'm actually talking about. I hope that I'm well understood audio-wise. I do have an accent. If this is a problem, I can't really address much more than I'm trying to already. All this being said, I hope that the lectures are understandable. They are good on an audio-visual level, and you are following the material well. Then there were further some discussion board entries on the posting of the answer of the solution for the lab in class 2. This was posted in the meanwhile. I hope this has been reviewed by all of you, and there are no open questions. If there are open questions, please post them to the discussion board. Let's continue the conversation on the discussion board. Thirdly, there was the question about the intercept, the way how you putting the intercept into the linear regression model function in R. So you can add this as a 1 plus the respective terms. That's one way to do it. And the reason why you would do it is because by default it's a +1, right? By default you always get the intercept. But if you convert this +1 to a -1, essentially it becomes a different function that suppresses the intercept, which changes the interpretation, obviously. So for this being said, it's just an expression of the default setting, essentially, that allows for a depiction of the linear regression model in a way that it reflects the mathematical form of displaying it. Good. I hope this was sufficiently explained at this point. Then there was a question about the percent bias reduction. I hope this is also clear in the meanwhile. So it's so the idea behind the percent bias reduction is really that if you use different levels of adjustment in a regression model, you get essentially a bias reduction. And from that end, this is what you mean to display with this formula. So when there was the question about omitted covariates, is essentially what was meant was like what's the difference between one versus another. So at this point being is like either model, either the one with the additional covariate or the one without the additional covariate is perfectly fine for the lab. So I think both is fine, and I hope this was also sufficiently addressed in the discussion board. So thank you for posting all these questions, and I really appreciate we have here an interactive, ongoing discussion about topics, and I think this is super, super important. Good. Hope the progress is well so far. We're going to do a couple of more topics in the realm of regression analysis today, and yeah, so let's dive right into it. So I will be sharing my screen now. So, okay, so now you will see my screen here on the right. Okay, so it's on the right, and that's why I'm looking to the right. So it's a larger screen. So that's why I always constantly look in the right side and not directly in the camera. So forgive me for that. So now you're seeing my screen, and essentially, are you seeing the right screen? Let me just double check that. Let me make sure. Now we want to see this screen. Yes, I think you should be seeing the right screen. Okay. Yes, that's the right screen. Okay, good. So again, please create a class 4 folder, create a subfolder with lab and lecture, add the lab files that I have posted with the SAB file. Those of you who have already a little bit of experience with statistical programs know that the SAB file is a SPSS file. And we will be opening it using the Haven package. And there are a couple of different packages how you can do it. It's the forum package, the Haven package, there are a couple of different. Then there's the RMD file for the lab, and sorry. So then we have the lecture file, which essentially contains here the RMD file that I've posted. Okay, so we're double clicking the RMD file. We're opening the RMD file up. And as you can see here on the right, I have already played around with it. So I'm emptying this RM list equals ls is how you clear everything. And let me actually explain why. So I had a couple of good meetings this last week with some of you. There was some suggestion that the basics need to be discussed in more detail, and therefore I'm gonna try to do better to really talk about the basics, but I really encourage you. So, so one of your classmates actually came up with the idea to create a function collection. I think this is a fabulous idea. So please do that. Keep me posted, loop me in if you want me to talk about the function in more detail. I'd be happy to post little videos specifically talking about functions. Also happy to elaborate on it in the discussion, but per se, give examples. But also you will see whenever there's a function you want to know. So I was showing the RM function, right? So now if you want to know more about the RM function, whatever that function means, you just go in the console. So again, here you have console, terminal, R markdown, jobs. Forget terminal, you don't need terminal for now. Jobs, likely you won't need it right now either. You may need it later on when you have jobs that are going on for a long time. R markdown is obviously the R markdown that we have worked with, and the console is R. So that's the core engine. So question mark RM or question mark any other function essentially allows you to look at this function. So it's remove, it's the remove function. And here's the package shown. It's from the base package, which is base R. And here you have all arguments and all details. You have examples at the end, so you can look up everything you want to have. And here's the function that I actually wanted to use. So RM and in brackets list will essentially give you the opportunity to list all the objects you want to have removed. So if I make A equals C 1 2 3 and B equals C 1 2 3. So now I have A and B as objects in here, small little vectors. If I do RM list equals C, A and B, object one not found. Okay, so that was not good. List equals A. Now I'm missing a bracket. Okay. Whenever you want to show something. Okay, list equals CA. Object 1 2 3 not found. Okay. So this seems to be a little bit more complicated. Okay. Anyways, RM A and B will delete our A and B. Good. So this is how you remove specifically objects that you want to remove. And it's always good to kind of keep a clear, a clean environment, because otherwise it's really getting messy. It's like if you have a long analysis with thousands of lines of code, and I don't know how many hundreds of objects you may have, you can imagine this gets really messy. So RM is actually really a function you want to keep in mind. So with RM in brackets and specific objects, you can remove the specific object. And yeah, so this is the RM function. And then you can RM list equals ls will allow you to delete or remove every object that's currently loaded in the environment, which is super useful. So, but now ls, just for you to understand, ls empty brackets gives you every object, gives you basically a list of all of this. Is nowadays in our studio not that important anymore, because essentially you have all of this here listed anyways. But back in the days where you only had base R, this was actually super useful because you kind of had an easy way to always get an overview of what objects are currently floating around in your environment. Where this function also becomes very important is if you want a list of all these objects that are currently in your environment and you do A equals ls, you get a list of all the environments, of all the objects in the environment in your object A. Okay, so this is just A smaller than hyphen ls. So this gives you a list of all objects. Good. All right. So what did we want to do? We want to clear the entire environment with list ls brackets. Done. Okay, good. What's next? Next, we want to get started with our file here. So please make sure that whenever I upload more than just the RMD file, include every file in the same folder, because sometimes it needs an additional graph or whatever. Now, this is not the case here. Need to PDF beamer should now do all of this, okay, and create PDF file. So this is today a very important lecture, essentially, because we will be talking about a topic that is extremely important. We will be talking about how to interpret in access to continuous variable, not only how to interpret regression models even further, but we will also talk now about in access to the continuous variable included in regression model. We will now also look at binary and polytomous variables, dichotomous and polytomous. So essentially you have binary or dichotomous basically has only a 0 and 1 kind of coding. So it's like either somebody is presenting with a high blood pressure or not. Either somebody is female or not. Either somebody is presenting with a high body mass index or not. Either somebody is, I don't know, is contagious in terms of COVID-19 or not, or somebody ate the nauseated, the nauseous eggs and the egg salad, and became nauseated after or not. So it's that kind of thinking that you have to employ for binary variables. When you have polytomous variables, you essentially have more than one level. So this makes a difference, as you can imagine, conceptually as well as analytically. Consequently, you need to also treat them differently, and this is what we will be discussing today. So we have quite a lot to discuss today, and I hope everything from the previous classes is kind of quite easily understandable, and all of you have a good handle on what we discussed. So while our marks done, so this is taking longer than expected. So we've gone fast forward. I don't know why that is the case, but yeah. Oh, yeah, here we go. All right, so maybe in the meanwhile, while this is all setting up, I can briefly talk about the syllabus. So since we're doing recorded lectures only, we are somewhat flexible on various terms. Some of you have gotten with me already on some, yeah, since I'm seeing it right in front of me, there was a little bit of a mix-up with my email address. So please forgive me for that. Make sure that you use the right email address. It's a secret announcement, and the current syllabus carries the right email address. I'm monitoring 6 email inboxes and working with so many different email inboxes, so I get confused with that one. That was actually my old domain when I still was a student myself. No, wrong. That was when I was a teaching assistant in 2018. So yeah, the domain has changed. There was an evolution over time, and for that very reason, I kind of slept on that one. So forgive me for that. So we have 920. We're talking about the linear model with categorically covariates. We will be doing lab 4. So we are slowly carrying on. Please make sure to not forget the exams, exam 1 on 1018. And exam 2, which is here on 1206. Keep in mind that this is coming up, and there are the research notes and the homework. So you will get these posted in a timely fashion. I will be in touch. Good, and let you know what is to do and when. Good. Okay, today linear models with categorical variables linked to ANOVA and ANCOVA. Good. So we are diving right in. We are now looking at biostatistics. Good. So we are looking at class 4. Let me just confirm that I can share the right screen. Just let's make sure everything is fine. Okay, so this is class 4, September 20th. Okay, class 4. So we will be talking about linear regression with categorical covariates. We are looking at dichotomous categorical variables, polytomous categorical covariates, and then we briefly talk about the connection with ANOVA and ANCOVA for a factorial experimental design. We will be discussing R for a categorical covariate, employing the factor function, and defining reference groups. We'll talk about this more in the lab, but I will get started briefly on that already in the lecture. So really thank you again to Hongbin Zhang and Marcel and Pino for providing us with all this wonderful material. So you're really in for a really super lecture today that really will outline what you're doing, what you have to do, and how you have to treat binary as well as polytomous categorical variables in real life. So I remember when I had to learn that, for me, it was a little bit more hands-on approach. It was in the context of survival analysis already. So it was a little bit more tricky, I have to say. So it's didactically, what you're being presented here by Professor Zhang is really very good material, very didactically valuable. Good. Lab 4, we will be talking about if-else conditions and factorialization of data. Good. All right, but enough of this. So 2 independent samples. We have 2 different groups. We have 2 subsamples. So it's not really, so we have a sample population that essentially in its dynamic is being used to study dynamics and to infer dynamics in the population based on the dynamics in the sample, under the assumption that the dynamics in the sample are generalizable to the population. So now in the sample, you also have subsamples. These subsamples can include features such as gender, can be male versus female, can be drug versus placebo, like you see down here, drug versus placebo, treated versus control, classic. But then you would use different analytical methods. But essentially, that's what it is, right? You have a sample that has a distinguishing difference in it, which is only rendering this to a 0 and a 1. So either present as a feature or not present as a feature. Okay, so we have drug, placebo, treated, control, low BMI, high BMI, male, female, smoking, non-smoking, etc., etc. So there are a million of these binary kind of factors around that can be employed here as as an example. So what does that essentially mean? So we are basically now looking at yi, which is our response variable, in the presence of x, which is here our binary variable, equals 0. So we are essentially looking at a beta 0 that is normally distributed with a variance around the mean. So this is basically characterizing the sample population or the subsample population from 1 to n 0. So of all n's that are included, so of all individuals that are included in that subsample. So now if we are doing the same thing for yi for the response variable for the subset where x equals 1, so for those that are treated with the actual drug, those that are treated, those that have a high BMI, those that are male or those that are female, or those that are smoking or non-smoking, etc., etc. So we're basically looking at beta 0, which is the same as these, plus a beta 1, again with a variance around the mean. And this goes from I equals 1 to n1. So this is the sample size in the subsample where x equals 1. So now rearranging this is essentially nothing else but yi equals beta 0, is beta 0, plus beta 1 multiplied by xi, which is either 0 or 1, plus the error term, which is our variance. Right? And the error term is essentially nothing else but a normally distributed variability around a mean of 0 with a variance of sigma square, standard deviation squared, variance. So, and this goes from I equals 1 to n. And this is now n equals here, n 0 plus n1. So where xi is a binary variable, which is either 0 or 1. So this is essentially, so you can call this X, whatever you want to call it. You can call it covariate, you can call it exposure, you can call it predictor, independent variable. So this is more of a use case kind of scenario. So you call it whatever you want to call it in the context, and then wrong, because that was a little bit too casually expressed. So you're not calling it whatever you want to call it. You're calling it what is appropriate in the setting of what you're using this covariate for. So covariate is the more kind of very specific kind of general terminology. Exposure you would use when you are actually looking at an exposure. So when you're looking at drug versus placebo in an epidemiological sense, you would use exposure if this is really your exposure and you're really looking at the exposure outcome relationship, then you would use exposure. If you're using, for example, I don't know, you're using it as an outcome in a multivariable regression model and you're just looking for one additional risk factor, then you call it a risk factor. And you're saying, okay, so the risk of cardiovascular outcome caused by 10, 15 different parameters, and smoking is one of them, then it becomes a risk factor. It's not really predicted at this point. It has predicting qualities, but risk factor is probably the more accurate term to use. But again, the epidemiologists may disagree with me, and I'm just saying on the use cases, you would choose the terminology that's most appropriate. Independent variable, also just like covariate, more of a more conservative, kind of more generally applicable term. Exposure, it really depends on the exposure versus predictor, all depend on the research question. Good. Okay. So next. So mathematically expressed, what we have looked at here, excuse me. Mathematically, we have looked at beta 0 plus beta 1 multiplied by xi, which is either 0 or 1, plus the error term, which we see here. If we're simplifying this, we're essentially looking at a plus b multiplied by x plus e. Good. So now we can estimate from this equation 3 beta 0, and beta 1. In R, this would be formulated like this. Add the 1, the +1. Professor Sang has added this pretty much every time he's coding for that. And I tend to agree with him that it's the proper thing to do, because even though it's the default, it's always good to kind of be very precise in what you're meaning to show. And this is true in the way you're coding, the way you're commenting, the way you're structuring your code. Precision and a clearly defined structure that leaves not much ambiguity of what was done and what was meant and what was intended makes things much more easy in terms of replication. And replication is important because last time I brought the example, I think it was last class. Last class I brought the example of you submitting an article to a journal. You're getting revision round 1 or revision round 2. 6 months later, you're getting that journal, that article back from the journal, like reviewer 3 was annoying and he wants new analysis. You need to go back to the code that you haven't touched for 6 months. So now you're basically going through your code and you're trying to decipher what you wrote 6 months ago when you were under stress and you wrote your last line of code at 2 a.m. after the 27th coffee of the day, and you don't recall what you intended to do there anymore. If you would have then 6 months earlier written any kind of comment that was not leaving any space for ambiguity, you would have said thank you 6 months later. Secondly, replication. It is good coding practice. It is good analytical practice that whenever you have an analysis of gravity, importance, and value, you will always have somebody else review it. This is usually within a team. It's usually the managers or the supervisor's task to kind of coordinate that you have like, okay, so you have analyst 1, works in this analysis for 6 months, and then you have like analyst 2 goes over it before this is being submitted to a journal as a report to stakeholders, to the FDA, whatsoever. Second set of eyes should be looking at this. Can be done in collaboration with analyst 1, because analyst 2 may have questions, but it's always important to write this in a way that anybody else can look at this code at any point in time and still make some form of sense out of this. This is, don't use abbreviations nobody else understands. Don't use your own kind of acronyms. Use generally applicable terminology. It's usually team-specific terminology. So within the team or within the greater team, usually you get acronyms and terminology together that basically everybody will understand in the greater team. So this happens quite naturally, usually in a lot of discussions and a lot of correspondence. But yeah, when you come newly to the team, then it's a little bit of a stretch, but you will pick up on it. People will show you, will tell you, right? It's part of the training process. You learn the language and you learn the culture of the team. But yeah, in essence, this is what happens, right? So I think it really makes a lot of sense to kind of comment well and be very precise in your commenting. Okay, so now I rambled on. Okay, so so this is the reason for the +1. If you make this +1 a -1, it will suppress the intercept, becomes a whole different volume. Good. Assume the estimations are beta 0 equals a hat or b hat multiplied by x. Good. What does that mean? Okay, so we are predicting now a y hat. It's a predicted value of y. This is our function. Right? We're predicting a response variable based on the independent variable on the x-axis. So it's y-axis as a function of x-axis. We have the scatter. Think of it as a scatter plot. We have the scatter all over our scatter plot. We have on the y-axis, we have a certain form of line. This y is predicted by the values on the x based on what we will see next lesson was the actual fitting estimation, fitting algorithms. We will see this quote unquote fit line. So this predicted y here is predicted by the interplay between a hat, which is, as we know, that's our a, that's our coefficient, right? This coefficient we're getting out from our LM. So this is the BMI. And then, no, this is, sorry, this is the intercept. And then we have b hat multiplied by x. So whether yes, 1 or no 1, or 1 or 0, 0 or 1. So this is exactly this. So beta 0 is our a hat. This is the predicted value when this condition is 0. And then we have beta 1 multiplied by x1, which is, if this becomes 0, you have the coefficient, any random coefficient multiplied by 0 will become 0. So it falls off. And here's the example of that, right? So now we have last time we have discussed the continuous variable. So we're talking about y hat equals 134, comma 802. Good. Plus 1.864 multiplied by x. So we have now systolic blood pressure comes at an intercept of 134. So if x equals 0, or was that decentralized? I'm not sure anymore. So you can either centralize it, and this will not show you, right? You don't know at this point because the coefficient remains the same, the intercept changes. So if this is a centralized kind of value, this would need to be explained. So if you have now 134, and with every increase of serum glucose, you will have an increase of 1.864. So this needs to be decentralized because 134 blood pressure is already considerably high. If you have a mean of, if you're starting off with a 0 and this intercept would be where x equals 0, and this is now how you get to using and interpreting this right away. So you have an intercept, which can either be the centralized value, or could be the actual intercept where x equals 0. So if this is 134, and you're having here serum glucose is at 100 to 120. If you have an increase of 1.864 millimeter Hg with every milligrams per deciliter of serum glucose, with 100 milligrams per deciliter of glucose, which is a normal, super perfectly normal blood glucose, you would have an increase of 2 zeros to the right. That's so the decimal 2 spots to the right. So essentially, you're looking at an increase of 186. So this is not possible as a value for blood pressures. So for that very reason, it's a centralized intercept. So continuous variable. So this is how you essentially quantify your y hat. Yeah. And this is beta 0, this is beta 1. Good. Now, dichotomous variety. How are we going to do this now? So we know that body mass index affects systolic blood pressure. It does affect systolic blood pressure. This is an interesting conversation piece, actually. So it goes a little beyond the scope of the conversation, but it's like, so there are various explanations why it actually affects blood pressure. But yeah, higher body mass index, people with higher body mass index do indeed have higher blood pressures, and there are various theories why that actually is the case. Interesting theory is hormonal. So there are hormones that are basically being secreted because of higher fat mass in the body. Secondly, fat is highly vascularized, meaning that it increases the overall diameter of existing vessels in the body quite substantially because there's so much vascularization in the fat tissue, and so much vascularization will require much higher cardiac output to essentially maintain a blood pressure that is supplying blood into all these additional vessels in the fat tissue. So now as a consequence to that, you essentially will also get other compensatory mechanisms increased that essentially will then in the periphery increase the blood pressure above what actually would be necessary, and therefore to maintain the blood supply to the fat tissue, you increase blood pressure in the periphery. So that's one of the zeros. So yeah, it's quite fascinating. But yeah, it's a very consistent kind of association that you will see basically in all analysis. So I'm flagging this for all analysis that you will be doing at one point in your time in your education, or also later on. Higher BMI always comes with a higher risk of blood pressure, higher blood pressure. Good. The cardamom is categorically variable. We have 225, which is a tremendously high blood pressure, but doesn't matter. Plus 6.559 multiplied by AX. Okay, so we have systolic blood pressure, Y0 here is, or beta 0 is 225. If the BMI is high, that can additional 6.6 millimeter Hg in addition to that. Again, so these are examples that are not necessarily found in real life, but again, it's an example. Okay, so the expected group difference, high versus low, is 6.6 for the target population on average. Higher BMI increases blood pressure by 6.6 units. Good. So this is fairly clear, right? And quite logical to understand, I find. So, and now the if-else function. We will play around with this a little bit in the lab. So if we're recoding now BMI into BMI2, BMI is currently coded in the RMD, in the Markdown file, that high BMI equals 1. So now we're recoding this. We're recoding this that that low BMI is now becoming 1. So we are having 225.855 plus 6.6. So if there's high BMI present, we're increasing blood pressure by 6.6 millimeter Hg. So what happened now? When you're recoding your BMI, you are essentially changing your covariate. So you have here as your reference category being those with a BMI that is low. And you're adding 6.6. If you're changing your reference category, you're coming to 2.32. And you're subtracting 6.6, meaning you changed your reference category and your beta 0 is now referencing a different subsample. So your reference subsample is not that group with the low BMI anymore, where you're adding the difference to reflect the blood pressure in the high BMI group. No, you're going the other way around. So right now your reference group is those with the high BMI. And if somebody with low BMI is being looked at, or you basically want to look for the mean BMI SPPs in the low BMI group, you're subtracting the 6.6 millimeter Hg. But that makes sense, right? So the beta 1 sign changed, so did beta 0. So beta 0 changed because it's reflecting now a different reference group. And this is important, and you will see why, because we're going to talk about this as well for the polytomous covariate, and it's the same story, right? So we have 225 plus 6.6. We have 232 minus 6.6. With the new coding, the sign changed, and so did the reference value. So we interpret the minus 6.6 as lower BMI decreases SPP by. And what's the interpretation of that now? With version BMI, 0 for low and 1 for higher, with version BMI according to this. Recalling how we interpreted with continuous X like this model. Suppose we found that age is confounding the relationship between BMI and SPP. What do we do? Okay, so this I hope is very clear. This is very central. So recalling how we interpreted with continuous model is like, yeah, so here it's essentially, it is the same story than with a continuous model, right? It's like if you would, you're adding or you're subtracting, and it goes in either direction, either positive or negative sign, and in that region, in that direction, your predicted y will change. Suppose we found that age is confounding the relationship between BMI and SPP. What do we do? Definition of confounder. So we had the conversation about age in the causal pathway between serum glucose and serum systolic blood pressure. And now we're spinning that a little further. So essentially we're having now the association between BMI and systolic blood pressure. So we have BMI being the exposure, systolic blood pressure being the outcome. The definition of the confounder would here essentially be age. We essentially have stratification or regression. So the inclusion of stratified variables does handle confounding to some extent. Regression can handle it as well. But for regression model, essentially we have an inclusion of an additional covariate as a continuous variable. So xi here essentially remains 0 or 1, and ci is the confounder. So we are including here h, and this becomes then a predicted y. So this is our beta 0. This is a. So this is for constant h and xi equals 0. Then we have beta 1, b1 or beta 1 multiplied by xi. So this is either 0 or 1. And then we have h. And the variance, which is, the residual error, which is n, around a mean of 0, with a variability of sigma squared. In R, you would code this as stated here. So, so here, don't forget, we still have here BMI2. BMI2, as we recall from here, is BMI2 is now essentially, keep that in mind, there were the high BMI is actually the 0. So we have changed the reference code. Keep that in mind in the interpretation moving forward. So once beta 0 and beta 1 and beta 2 are estimated, we have a hat, which is our predicted coefficient, our predicted beta 0, plus b1 beta, or hat, b1 hat, beta 1 hat, and beta 2 hat, multiplied by the confounder h. And y hat is our so-called predicted y. So just as a reclaimer, so we have, if you remember from introductory statistics, we have a y hat and we have a y bar. Y bar stands for the mean y, and y hat stands for the predicted y. I'm just mentioning this to make sure that this is clear. Okay, so this is our fit 3. We have now the 6.514. So this is now obviously different than what we had before. because now it factors in 6.559 versus 6.541. So this has changed now because age is a confounder in the causal pathway between BMI and systolic blood pressure. As a consequence of that, essentially, we see lower differences between BMI 1s and 2. So this affects the relationship. It still remains a significant relationship, but it changes the difference. And this is important. So if you want to interpret this, you need to say that this difference essentially is, all else being equal and age being held constant, the difference is 6.51. So we talked about all the interpretation and all these aspects before. The F statistic here essentially becomes interesting because essentially we are now looking at additional between group and within group degrees of freedom. The 97, as we remember, is always in the model the overall number. So this is a sample size of 100, I believe, minus the groups that have been studied. And so yeah, so 6.559. Now here, adjusted for age, we look at minus 6.514. So in terms of terminology, and this is important, this model 1, this fit 1, is referred to as a so-called unadjusted model. So lower BMI will decrease systolic blood pressure by 6.559 in average for the target population, whereas interpretation in an adjusted model decreases the difference to 6.514. So lower BMI decreases systolic blood pressure by 6.514 in average while holding age constant, as I said, as constant for the target population. Okay, I hope this is very clear, and I think it really outlines the difference. So the effect of age as a covariate in the model is here factored in already. What is just important, you need to hold age constant. So differences in age will obviously affect the interpretation and the predicted outcome variable and the predicted y. Suppose we found that besides age, education also confound the relationship between BMI and SBP. What do we do? Stratification would even be more complicated, but we can do a regression by adding EDU, education, as an additional covariate. How? Well, so now it's getting a little tricky. So now we have added confounding binary variables, which is easy, right? It's a 0 and a 1. So now with education, we actually have 3 categories. This is no high school, or college. We could just simply add such a variable in the model by saying, okay, A plus B1 multiplied by X and B2 C1 plus B3 C2 plus E, where C2 is a categorical variable like EDU. We could hypothetically do that. It's not the right approach. You cannot do that. Why can you not do that? Because essentially you have more than 2 categories. So if you do it with 0 and 1, it becomes very easy because as soon as you multiply the coefficient beta 1 with 0, that drops off arithmetically, right? It becomes 0. And plus you add the 0 to a value, that becomes non-informative. If you have now 3 groups, you need to have a different coefficient for each grouping, keeping 1 as a reference group. So essentially, we need more than 1 coefficient. And this is usually done with something like that is called a so-called dummy variable. A dummy variable essentially stands for the coding of the respective characteristic you want to express. So if you have the characteristic not a high school graduate. These are those that don't have high school, don't have college. You basically create that as a reference value. You basically do condition 1 is 0, so you basically have zeros for everybody that did not attend high school or college. So if you have high school but not college, you create an R1 for those that did high school but not did college. So you create 2 of these dummy variables, and you get 0 and 0 for those that did not get into did not do high school. So both in R1 and R2, these are zeros. R1 will be a 1 for those with high school, but not for those R2 that codes for college graduates. So now the other way around, for college graduate, they only have a 1 in R2, but they don't have 1 in R1. So R1 basically reflects the high school, but not college people, whereas R2 reflects only the college graduate, whereas a 0 on both R1 and R2 stands automatically for not high school graduates. So now including this in our model will basically result to beta 0 plus beta 1 multiplied by BMI, what we have as a 0 and 1, plus beta 2 multiplied by age as a continuous variable, plus beta 3 multiplied by R1, which is our high school graduate, and beta 4 multiplied by R2, which is our college graduate, plus the error term, which is normally distributed around a mean of 0 with a variance sigma squared. So consequently, the reference group here is that with all zeros. Right? So our reference group are those that are not high school graduates. So coding this into an EDU D1, and we will do that in lab, EDU D2 will essentially result in coefficients for EDU D1 and EDU D2, which essentially will now have an effect on the systolic blood pressure based on their educational level. So the question is, do we need to interpret this minus 0.617 and the minus 4.42? We can if it's relevant, but we don't have to because it's already factored into all the other coefficients. So this will still be our beta 0. And if we're still only interested in the body mass index, here we go. That is the actual body mass index after factoring in education and age. So from 6.559, we came from 6.541 now to 6.327. And this is the according and the model that essentially leads to this result. So now we can recode this without a problem. So now we have as a reference group with the non-high school graduates. And now we're recoding it, that we're recoding it to college graduates. And then we're essentially looking at additive effect, where basically, if you're not a college graduate, you will actually have a strong effect on blood pressure because you're probably unhealthy and you're different socioeconomic levels of various reasons. But that's an interpretation question. Okay, so this is this. So you can recode this and you can use a different reference group. So yeah, this is essentially what I said, right? It's different reference groups that essentially now will allow for you to essentially allow allows for you to essentially interpret this differently. It does not affect the coefficients of BMI and age, which you can see here, right, logically, because these variables have already had the effect on both the beta 0 and the beta 1 and the beta 2. And so now with the beta 3, essentially, this is only changing within the framework of beta 3. So if you recode beta 3 and you use a different reference value, this will not affect the interpretation of the other coefficients, only of the coefficient of which you're implying the difference of coding. So the question is, what is the beta 0 under the two codings? Don't forget age. What is the beta under the two codings? Yeah, well, it's the same beta 2. The only thing that changes is now that you will need a different reference group that you're referring to. So essentially your SPP head is here 216 for BMI2 is for the low. So this reference group are the high BMI guys. So this is now BMI2. If this is 1, then it's a low BMI. So this is basically it's dropping down the blood pressure. This is being held constant. And then we have these here, which the reference group is the not high school students, right? So basically, if you are a high school student, it basically lowers it. If you are a college student, it lowers it. So essentially, the interpretation here of the 216 is this is for high BMI students at a constant age with no high school degree. Okay. Whereas this here, where we have changed the reference group, to reflect, and this is actually this I need to change. Yeah. Where the reference group, no, actually it's fine. Okay, so, okay, doesn't matter. Okay, so where the reference group is actually college graduates. So this BMI is actually 212 for those with a high BMI, constant age, and being a college student, being a college graduate. So if you were a high school graduate, you would add. If you're not high school, no college, you add even more. So this is this clear. Okay, is this clear? It's really, it comes down to which are the reference groups for you to interpret your beta 0. Don't forget age needs to be constant at either where x equals 0 or at the mean if you do a centralized age. So these are the respective models, and you can also convert this into a factor. And essentially this we will also do in the lab. So the factor allows you to actually create factors for each level of what you're using it for, and then you don't need to create dummy variables, which is very nice because that allows you to kind of bypass the need to create dummy variables. Interpreting a little harder. No, it's actually it's the same, because you see here with the factors, it's the same coefficient, right? It's it's the same values. It's 6.2, 4.42. It's the same values. Just gotta make sure that you're not getting confused about things. Yeah, it's essentially it's a very elegant way to approach it. So I'm using it quite a bit. So linear regression models outdate ANOVA and ANCOVA. So we know that a one-way ANOVA is a linear regression with one independent categorical variable. We have talked about this, right? This is also why employing the F statistic in the categorization of the effect size of the ANOVA, the R squared. if you have a two-way ANOVA, you have two independent categorical variables, which is essentially what we did today. And the ANCOVA essentially is an ANOVA with continuous variable, which essentially we have done with, including the age. So it's really linear regression actually brings ANOVA and ANCOVA to another level and essentially allows to use a much more efficient analytic approach. And we will be talking about the enhanced data today. We will fit the multivariable model, describe each variable numerically and visually, which is meaning a summary and a histogram. We describe pairwise relationships between study variables and outcome variables. We are looking at an education variable. We will create dummy variables and factor functions. And I will be soon back with the lab. And I hope you found this lecture good. I look forward to the discussion on the discussion board. And I think it's very important as a topic and definitely something that you will be exposed to quite frequently. I'm certain of that. Okay, sounds good. Okay, so I hope you found the lecture good and useful. And I will be awaiting your comments on the discussion board, and I will be right back with the lab.